In this module, we will be talking about color. Around 350 BC, Aristotle wrote Meteorologica, stating that colors come from darkness added to colorless or pure light through interaction with the four elements: water, air, earth, and fire. The next mention of color is in Leone Battista Alberti's treatise, De Picture, published in 1435, followed by mentions to color in Leonardo da Vinci's notebooks. But it's not before 1672 that the modern color theory really starts with Newton's new theory of light and colors, where he describes his 1665 experimentum crucis with prisms. Following that, in 1704 to be more precise, Newton published Optics, or a treatise of the reflections, refractions, inflections, and colors of light, the first time ever that the physical properties of color are given a definite scientific explanation. In his Experimentum Crucis from 1665, Newton used a prism to refract light into its constituent colors. Not unlike a rainbow, which is caused by refraction and dispersion of the sun's light by water droplets. White light is not pure after all, as Aristotle thought, but composed of 7 separate hues: red, orange, green, blue, indigo, and violet. Inspired by Newton's discoveries, but also by the work of chemists Charles Dufay and John Hallote, George Palmer, a chemist himself, states in 1777 that the nerve fibers in the eye's retina are made of color particles. According to this hypothesis, each of these particles would absorb rays of light corresponding to red, yellow, and blue. Between 1802 and 1850, Thomas Young and Hermann von Helmholtz come to the conclusion that the eye's retina doesn't quite have color particles, but consists of photoreceptors sensitive to red, green, and blue instead. The Young-Helmholtz theory, otherwise called the trichromatic theory, was born. This theory set the basis for the scientific additive color synthesis model, still in use today. In 1855, James Clerk Maxwell created a device to demonstrate the trichromatic theory, a color top, as the one in the image. Before that, he would give mathematical proof to this theory. It was empirically demonstrated again by physiologist Gunnar Svedichin in 1956. Svedichin also confirmed the opponent color theory proposed by Ewald Hering in 1892. The opponent color theory states that the perception of color is the result of the processing of 3 pairs of antagonist colors: red-green, yellow-blue, and white-black. It was originally formulated in opposition to the trichromatic theory. The two theories are in fact correct. Again, in 1855, Maxwell proposed a way to superimpose 3 black and white slide positives with 3 colored filters projected by 3 separate lanterns on a screen. In 1861, along with photographer Thomas Sutton, Maxwell created the first ever color photograph using this method. The electromagnetic spectrum is comprised of charged particles that exhibit wave-like properties such as radio waves, infrared, ultraviolet, X-rays, gamma rays, and microwaves. Visible light is electromagnetic radiation too, a narrow band within the electromagnetic spectrum. Each band within the electromagnetic spectrum possesses different properties: wavelength, photon energy, and frequency. Wavelength is inversely proportional to photon energy and frequency, while frequency and photon energy are in direct proportion. The higher a photon's frequency is, the higher its energy is, whereas the lower the frequency is, the lower its energy will be. A couple of examples would be gamma rays, which have shorter wavelengths but are highly energetic, and radio waves, which have longer wavelengths but have low energy. The sensation of color is a product of one's brain. But first, visible light needs to reach the photoreceptor cells in the retina. There are 2 kinds of photoreceptors in the retina of vertebrates: cones and rods. Rods populate the outer edges of the retina. They are sensitive to lower light conditions. They are also responsible for peripheral vision and the perception of movement. Cones, on the other hand, populate the center of the retina. They are responsible for the perception of color. They are also responsible for visual acuity. There are 3 cone types in our retinas. They are either sensitive to longer wavelengths, in the red band of the electromagnetic spectrum, or shorter wavelengths in the green-blue band. In 1916, Japanese ophthalmologist Shinobu Ishihara created a series of tests that he used to identify color blindness in patients, otherwise called the Ishihara color tests. The principle is simple. The test consists of several plates, each with a disguised number made of close-colored dots of different sizes. The physician will show a number of plates to the patient, and the number of correct answers will generate a score that will help identify the severity of color blindness. The additive color synthesis model for mixing colors follows the Young-Helmholtz model or trichromatic theory. The primary colors in the additive color model are red, green, and blue, also called RGB, which are the constituent ingredients of white, meaning that combining red, green, and blue lights in equal amounts will produce white. If instead of passing beams of light through 3 separate color filters, which is what you would do in additive color mixing, you were to pass a beam of white light through the same filters, now overlapped, you would get subtractive mixing. This image demonstrates additive and subtractive mixing using ideal cyan, a bright lively greenish blue, and yellow filters. Adding cyan and yellow light gives greenish white light. Subtracting blue and red from white light with cyan and yellow filters gives saturated green light.